images using filters and masks, to be taken by Pranav Sharma, Ayushi Ghoshal, and Sidvit Warik.
Let's dive right into the amazing session. Over to you, speakers.
Right, guys. So I think we should start. So, well, hello, guys. Pranav here, and I hope all of you are doing good and are in pink of your health. Also, guys, I request everyone to stay at home, defeat the virus, and also enjoy the beautiful events that the AI Club has arranged especially for you. Today it is 28th July 2021, Monday, and beginning of our week two of our CV week. And today with me, my amazing speaker friends Ayushri and Sidwade will be talking about masks and filters and edge detection. I can assure you right away that if you pay your complete attention to this session, you'll possess a great amount of knowledge and see the world in a different way. Also, we have an amazing cartoonifying project at the end, which is like the most coolest thing. So I urge everyone to stay with us till the end, and we will make this session a magical one for you guys. All right. Without any further ado, we will start with our session. Now, before going into the concept of masks and filters, we will have to learn about a terminology, which is very important part associated with this concept, and we call it convolution. Okay, so convolution is a simple mathematical operation, which is fundamental to many common image processing operators. Convolution provides a way of multiplying together two arrays of numbers, generally of different sizes but of the same dimensionality, to produce a third array of numbers of the same dimensionality. Now let's look at this GIF and understand it more clearly. Here we have a kernel. Now what is a kernel? Well, a kernel is a small matrix which is used for blurring, sharpening, embossing, edge detection, etc. etc. Okay, now spoiler alert. The kernel is also known as a mask or a convolution matrix. Now, what we are basically doing here is multiplying similar entities and summing them together to get a desired intensity of the target pixel. This is what convolution means in image processing, and that's simple how it is. All right. Now let's move on towards the concept of masks that we have all been waiting for. Now, guys, a simple question for you all. What is a mask? I'll give you 2 minutes. You can type it in the chat box and then we'll continue with the session. Sit with next slide. I'll wait for the answer, guys. Okay, that's a good one. Okay, so I'll break the suspense for you guys. All right. Now, for all those who thought this is a mask, I would say wonderful, +1 for your sense of humor. But what I was looking for was this. Next slide, Sadhvi. Yeah, a mask in 2D form is nothing but a matrix that we convolute over image to obtain the desired blurred, sharpened, or embossed image. Now, it is very similar to the mask you saw in the previous slide that we wear over our face. The way we wear masks during these times over our face to cover our mouth and nose, and how it changes the way we look. Now, masks in computer vision are similar. Suppose an image wants to wear a mask and change the way it looks. It can't just simply pick it up and wear it. It has to convert the mask over its pixel to change the way it appears. And this process of convolving a mask over an image is also called masking. And that is how simple a mask is. Now, I hope you guys understood what a mask is. Now, we'll move on to the next topic, that is filters. Okay, so what is a filter? Now, I'll make it easier for you guys. A mask is a filter. Wait, what did I just say? Exactly, a mask is a filter. So basically, a mask is a more general kind of terminology. Now, it can be understood by a very simple example. Suppose a person comes to India and he says, I'll be visiting India and seeing Taj Mahal. Now, this set statement resonates with masks in our concept. And when the person says that I'll be coming to visit Taj Mahal, which is in Agra, this statement refers to a filter. Now, a filter is basically a more specific application or terminology that we are looking for. What we want to smoothen the image, we use smoothing filter. When we want to sharpen the image, we use sharpening filter. And applying these specific filters to our images is what we call filtering. This is the concept of masks and filters in a nutshell. So congratulations, guys. You're now through your basics of filters and masks. And now I would like to call upon my very talented speaker friend Ayushi, who will be talking about the types of filters, which will be very important while decoding the Cartoonifying project. And Ayushi, you may take over, and I'll see you guys in a while.
Thank you, Pranav. That was an amazing session taken by you. So, good evening, guys, and hope you all are keeping well at your homes. And before we begin with the session, just a disclaimer for you all that, guys, in this session, we have decided to include some theoretical aspects. We are doing this because of the projects that we have included. They have certain terminologies that you would understand better if we explain it to you beforehand. So, and also if the bar is set pretty high by the previous sessions by our amazing speaker friends, the previous 1 week of tediousness brainstorming sessions that we all had. So the bar has been set up too high and we'll try to match that level also. So without wasting any time, let's move further with the concept of filters that Pranav just now, gave you a small introduction about. So computer vision is everywhere in our daily life. Okay, so when we are talking about the term filters in general, now what is the first impression that you get inside your head when you just hear the term filter? Like you would get something in your mind like this. Sidit, next slide. Yeah, you would get something in your mind like this. So we see all these kind of filtered photos on our various social media platforms and articles and magazines and everywhere. But here we are focusing on computer vision terminology filter. So focusing on CV, the term has turned out. So you might have known till now, after 1 full week of sessions of on computer vision, that images are nothing but functions that are mapped with pixel values in the form of a two-dimensional array. All right, guys. Images are transformed into two-dimensional arrays, and then the algorithm performs its operation on those particular images, and thus we obtain an output. So filters are basically a system that will enhance the image. Now, guys, the essence of filter is very same as to what the terminology filter means to you in the I'm talking regarding to the social media point of view. So the essence is same. Like our work of enhancing the image, that work is the same thing. But in terms of CV, the enhancement of image has a little bit of different definition. How is it different? That I'll tell you in the furthermost slides. Sit with next slide. Okay, so according to computer vision, when we filter an image, we can either blur that image, we could either sharpen that image, we could either remove the noises from that image. So anything that causes a change in the output image or enhances it, either blurs it, removes its noise, that is known as a filtered image. So in a nutshell, filters are used for image enhancement. All right. So now you will have that question in your mind that how are images enhanced? Like how do we do all these work of enhancing the images? So to improve this quality of image that we have, we basically, consider it in two domains, either the spatial domain or the frequency domain. So with the introduction of these two terminologies, let me tell you the types of filters that we are going to study today. So wait, next slide. Yeah. So there are two types of filters that include your spatial domain filters as well as your frequency domain filters. Now, guys, a small definition of the two. See, your spatial domain filter that includes a 2D array. Okay, that will include the pixel values that you have given. Like the 2D array, it consists of the pixel values. So your spatial filter deals everything with the arrays thing. But your frequency domain filter, it has Fourier transformation included within it. Now, with the introduction of the term Fourier transformation, you must have thought that, okay, we are going to include some mathematical stuff, but FYI, we are not including any mathematics because I don't want you all to turn out Aryabhattas and I don't want you all to bore any further. So all my heartfelt apologies to all the mathematics lovers. We are not going to include any mathematical calculations. It's just the theoretical aspects that we are going to discuss tonight. Okay, so next slide. Moving with the spatial domain filters. Now, for what reason do we use these spatial domain filters? Guys, spatial domain filters are also known as point processing. Okay, I repeat, they are known as point processing. Now, with the term point processing, see, in computer vision, things are pretty easy. Like you have the catch everything in the name itself. With point processing, you can easily make out that there is something to do with individual points. And that's exactly what spatial filters are. So spatial filters are known as point processing because they modify the intensity of every individual pixel. It considers each individual pixel, it modifies it. So therefore, all points are considered and all points are modified. And thus we know it as point processing. It's very simple. Your catch is in your name. So these spatial filters, they are basically used for two purposes. First one is for smoothing and the second one would be for sharpening. Now first we'll discuss sharpening and then we'll move to smoothing. Okay, so sharpening, as the term suggests, it sharpens the image. Now what do we understand by the term sharpens the image? It means that it will highlight the details of the image, all those details of the image that are either blurred due to some error that might have occurred or due to image acquisition, all those things will be highlighted. Okay, so that is the term of sharpening. Now you will have a question that how do we sharpen the images? See guys, when you have your two-dimensional array, you are going to take out its first order derivative. By first order derivative, I am talking about differentiation. Okay, so you're going to take out the first order derivatives of all the pixel values that you have, and then you're going to find out the maximum value among all these first order derivative values. Now, why are you going to find out the maximum value? Because your maximum value gives you the location of the edge. And why are we finding the location of the edge? We are finding the location of the edge because when you involve the sharpening filter for operation, your edges are enhanced, your features are enhanced, and it's for that reason that we are focusing on the detection of edges. The vivid description about edge detection is also there in the furthermore slides, but over here, just keep that concept in your mind that the maximum value of the first derivative will help you to locate an edge. All right. So, Sivid, next slide, please. Yeah. Okay, so as you can see in this image, we have the beautiful Lena, whom the computer vision enthusiasts love. Yeah, because she's so beautiful. So in this image, you have the original image of Lena, and then you have a detailed image. Now, if you focus yourself on the detailed image, you will see that all the edges are highlighted over here. Like all her features, everything, it's highlighted over here. And then we obtain the sharpened image by combining the original image with the detailed image. Thus, edge detection over here, it plays a very important role because once the edges are detected, if you place this image above your original image, you are going to get a more enhanced image where all your edges, all the features of Lena would be much more clearer, and thus you obtained a sharpened image. So for sharpened image, your highlight of the edges is very important. So in a nutshell, or just in one line to conclude, when you are going to focus on sharpening, you are going to enhance the features of an image. To enhance the features, you are going to detect the edges, and for detection of edges, you are going to calculate the first order derivatives, okay, and find the maximum value, because the maximum value will give you the edge. So this is the entire thing about the sharpening filters. So we'll pause for some time, and if you have any doubts or any confusion regarding this particular part, sharpening, you can go through or you can process it inside your mind. And if you have any doubts, you can put it in the chat box, and then we'll continue just after. Just take a few seconds break, and then we'll continue further. Any doubts, you can post it in the chat box, guys. All right. So since there are no entries in the chat box, we would move forward. Okay. So Sidvit, next slide. Yeah. So next slide is thus we have finished with the discussion of our sharpening filters. So now we are going to move, or we are going to talk about smoothing filters. Now smoothing filters are further divided into two: linear filters and its acronym, the non-linear filter. So smoothing. Now what do you mean by smoothing of an image? Smoothing of an image means you remove the noises and the image becomes more blur. Now, what are noises? That might, I think that all your curious brains might have got into the term noises till now, but don't worry. Noises are nothing but disturbance in an image. Now, how the image looks after noises, we have a picture for that at the end. So don't worry, all your doubts will be clear. Okay. So for the time being, just keep in mind that smoothing results in removal of noises. And once all the noises or all the disturbances you remove from the image, your image becomes more blur. Okay, so for this smoothing purpose, we use two kinds of filters. We have the linear filter and we have the non-linear filter. So in the linear filter, as Pranav just now told you about mask, we use a mask in the linear filter and then we perform the convolution operation and we obtain the output image. Okay, so what type of mask, or what is the more process that we are following here is we are using the averaging filter and the weighted average filter. Now see guys, again you have your catch in the name: average filter and weighted average filter. So average filter means that you are going to find out the or calculate the average, and weighted average would mean that you are going to have some weights attached to it. Now weights are nothing but numbers. As you can see in this second image over here, this where we have an original image that has its pixel value as 343, 544 and 112. It's given over here, and below we have the mask. That every description about the mask and all thing that has been told to you by Pranav right now. So we have the mask over here, and below we are calculating the average, or rather we are performing the convolution operation and all, and next we are getting a output image to be 3, and we are replacing the centermost pixel with that value. Now, similarly, again, we are going to follow this process and replace all pixel values with the average filtered value. And thus, we are going to obtain a new image. Now, that new image that we obtain, that is known as your linear filtered image. All right. And when we are, if we use the weighted filter, averaging filter, mask, here we are doing nothing but attaching some weights to our mask. Okay, like you can see, it's 1 by 16, then it comes 2 by 16. So this 2 is nothing but a weight that is attached to the mask of 1 by 16. Similarly, 4 by 16, it's there in the second row, second column. 4 by 16 over here, 4 is nothing but the weight. So in this way, we are performing the convolution operation, and thus we are obtaining new pixel values and we are obtaining a new linear filtered image. So that's all for linear filtering. Linear filtering includes a mask to get a new filtered image. Now, talking about non-linear filter. Linear filtering has a mask. So obviously, non-linear filter, being its acronym, will include no mask. Non-linear filter does not include any mask with it. So now you guys must be wondering that if no mask is included, how are we going to obtain the image? Don't worry. Your image is you're going to get your output image with the help of the neighboring pixels of that particular pixel value that you have chosen. For suppose, consider this second image where you have the original image to be 347, 542 and 113. So we have considered our centermost pixel value 4. We are going to replace it by using the non-linear filter. What we are going to do is we are going to arrange all the pixel values in ascending order. Okay, it's very logical. Just follow the logic. Okay, you are going to arrange all the pixel in ascending order. That's a common step. Now, if you are applying maximum filter, you're going to find out the maximum pixel value and replace the centermost pixel value with it. If you are using the minimum filter, you are going to take the minimum value and replace the centermost pixel with it. And if you are using the median filter, then you're going to take the median value and replace the centermost pixel with it. Okay, I'll repeat one more time. You have your 2D array. You're going to arrange all pixel values in ascending order and then check out for which filter are you going to using. If you are using maximum filter, calculate the maximum value and replace the centermost pixel with it. If you're using minimum filter, take the minimum value and replace the centermost pixel with it. If you're using median filter, take the median value and replace the centermost pixel with it. It's very simple. Just understand the logic. Also understand median filter, give a little bit of light upon median filter too, because this median filter, we have used it in our cartoonifying project that's at the end. So this median filter terminology needs to be understood properly. In median filter, we are going to consider the centermost image and replace it, and then we are going to perform the this operation until all our pixel values get changed, and then we are going to obtain the final non-filtered image. So this is how linear filters and non-linear filters process. Linear filters, you have a mask. Non-linear filters, you don't have a mask. And you arrange things in ascending order, and according to the filter, you pick and replace the pixel values. Easy? Simple? Okay. So now process this things and look at this image over here that it's presented over here, again of Lena, of course. So the first image that you see, this is the original image of Lena. The second image, where there are some disturbances or in the Lena image, these are nothing but noises in the image. You see how distorted the image has become. Now this distortion is known as noise. Okay, and in the third image, we have cleared some of the portion of noises from, or we have removed some portion of noise from this Lena's image, and thus the output that we obtain after noise removal is a bit blurred. So thus, you remember I said to you in the beginning that when you apply the smoothing filter, you are going to remove your noises, and that is going to make your image blur. See, I use smoothing filter on this particular image. I removed the noises and my image became more blurred. So that's the entire thing about smoothing, and that's the entire thing about sharpening. So we are going to process these things and we are going to wait for a few seconds. If you guys have any doubts, you can put them in the chat box. Just understand the logic, and you have your all catches there in the terminology. Once you get through the terminology, you're going to easily fix things out, and it's not as difficult as it might seem to you. So if you guys have any doubts, you can post them on the chat box, and we'll wait for a while and then we'll again begin. Okay, so linear filter again. All right. See, Sidvit, can you take back to the linear filter slide? All right. So linear filter, what we do is we are basically using a mask over here to obtain our output image. All right. So the concept of mask has been explained to you by Pranav. Okay. So you are having the original image matrix over here. You are taking the mask. Now that mask varies if you are choosing the averaging filter or the weighted average filter. Okay. So if you are taking the mask of the averaging filter, you are gonna perform this convolution operation with these values. Okay, like 1 by 9, it's multiplied by 3, so it becomes 3 by 9. 4, it's multiplied by 1 by 9, it becomes 4 by 9. So similarly, all these values are added, and at the end you're going to obtain one single number. So that single number that you obtain is your output image's pixel value. So then you will replace the centermost pixel value with this value, like 4 over here is replaced with 3. Now from where did we get this 3? We got this 3 from the average filter. Similarly, when you are using the weighted average filter, here certain weights will be attached in your mask. So all these weights are going to be considered, and then you will obtain your final number, and that number or that pixel value we are going to replace the centermost pixel value with. Like 4 is replaced by 3. So your centermost pixel over here is 4. And after convolving it with the mask, you are getting the output to be 3. So you are replacing the value of 4 with 3. So that's the entire thing about linear filtering. You are basically using a mask over here to obtain your image. But non-linear may you are not using any mask. Over there, you're using the neighboring pixels. So that's the basic difference, and that's all about linear filters. Is it clear? Okay. Okay, and okay, I have another question about how does bilateral filter work? Guys, bilateral filter ka mathematical calculation is a little bit very, confusing kind of thing. So that we have excluded since you are just in the beginning stage. So that's why we have excluded it. And if you still want some particular insight, then we can provide it to you after the session, I guess. Okay, so we'll continue. So this was the entire thing about the linear filters, your non-linear filters, and smoothing and sharpening and such stuff. So moving ahead, next slide, Sidvid. Sidvid, yeah. So as we know that all your this linear filter, non-linear filter, these all were included under the spatial domain. All right. So next you have your frequency domain filters. Again, you have your catch in the name. Frequency domain means you got to know that there is something to be done with the frequency component of the 2D array. Okay, frequency domain filters. Now, frequency domain filters, they basically use your frequency component. And why are we using frequency domain filter? That will be one question. That why are we using it? Because we already had spatial domain. So the scientists or researchers, they did not need frequency domain, but we have it, and we have it because frequency domain filters, they basically make the operations much more simpler because they have some mathematical calculations involved. So mathematics might seem tough, but it makes things much more simpler and easier. So frequency domain over here, it makes things much more simpler and it speeds up the process because guys, when we are using image, most of the image processing applications, like in real world, most of the image processing applications, they all are real time. So when any application is real time, you need an algorithm that gives you the result automatically, or the result is much more faster and easier. So for that particular thing, we require frequency domain filters, and hence they are given more importance or more weightage than spatial domain filters. Okay, so frequency domain filters, they are divided into three types: low pass, high pass, and band pass. Again, it's very simple. Just follow with me. Low pass frequency domain filter. In low pass frequency domain filter, just as the name suggests, you are going to keep the low frequency component and omit the high frequency component. All right. Low pass frequency may we are going to only deal with the low frequency component of the image. You have your 2D array. You're going to calculate the frequency of each pixel value. So from there, the least frequency of a pixel value, that pixel value you're going to keep, and the pixel value that has the highest frequency, you're going to omit that part. So that's the thing that we're going to do with low pass. Similarly, in high pass, the things change. It's just the opposite. In high pass, your name is only suggesting you the entire process. In high pass, you're going to keep the high frequency component and discard the low frequency component. And when we talk about band pass, once you discard the high frequency component, you discard the low frequency component, you are left with a moderate range of frequencies. So that moderate or the middle range of frequencies that you have, that is coming under the term band pass frequency domain filters. Okay, so talking about the application, low pass is going to smoothen things, high pass is going to sharpen your image, and band pass is going to smoothen as well as sharpen. Because low pass deals with the low frequency component, it will just smoothen the image, it will make the image more blur. Your high pass deals with sharpening of the image, means it's gonna detect the edges. And band pass, since it's not biased towards low pass or high pass because it consists the range of all moderate frequencies, is going to do both the things. So this is about our frequency domain filters. Okay, next slide. Okay, so up next we have one special filter. Okay, guys, please remember this is a special filter. This is the Gaussian filter over here. Now, why have we included this? Because this is included in your cartoonifying project also. So this Gaussian filter thing is used because again, we are going it involves much of a mathematical calculations because it basically is a probability distribution. Okay, so we are not going to discuss that aspect now because I don't want you all to become Aryabhattas again. We are going to focus on why are we using Gaussian filters and what is the main reason behind using it. So Gaussian filters are basically used for blurring the image and smoothing the image. Again, you'll be asking me that we already had linear filter for that. So why did we introduce Gaussian filters? Again, would be the answer that since mathematical calculations is involved and we are using all the probability distribution functions, so the output image that we receive, it has got some better results than the spatial domain wala thing. So that's why Gaussian filters are used. Its main aim is for making the image more blur and smoothing the image and removing all the noise. All right, this is to be done with Gaussian filters. So next slide, Sidway. Yeah. Last but not the least, you have the uses of filters. Now, I gave you such a long demonstration about the filters wala thing. So now we have that why are filters used for, or what is the use of a filter? So all these, applications of the filters, they are already I have discussed them, but once again, we'll revise them. Your first thing is it's used for image sharpness. It's okay. Again, sharpness means it will highlight the edges and will give you all the fine details, and it's used in photographic industries or the printing industries. There is the application of image sharpness. Please remember that this point, guys, because everything that we are discussing over here, it's going to be there in the quiz also. So if you are paying attention here, you're going to, enhance your quiz points only, and then and that would affect the leaderboard too. So after image sharpness, we are using filters for blurring, because I told you, but blurring is basically a pre-processing step of editing the image where the noises are removed. And the third point would be noise reduction, well, removal of noises, all the disturbances, distortions, anything that's present in the image, removal of that is noise reduction. And last but not the least, you have the edge detection. Now, guys, why is edge detection important? And I want you all to focus on this point, or edge detection, because edge detection is required for your cartoonifying project, because there, if you see the cartoonified image, only the edges are highlighted in that particular image. Okay, so edges are detected because you want because sometimes it can happen that you want to extract some region of the particular image, or you want to replace that region, sorry, remove that region, or color a particular region. So for extracting regions, or processing the regions, we are going to use edge detection for detection of edges. That is, it will find us for us the boundaries. Once we get to know the boundaries, we are going to divide the image into segments or into regions, and then we can perform our desired operations. Like if either you want to remove that particular segment, you want to color that particular segment, whatever you want to do, you can do with edge detection. So over till here, filters is complete. And if you have any doubts regarding filters, you can post them in the chat box, and we'll again wait here for give a pause for a few seconds, and then we'll move forward to a detailed description of edge detection. You have any doubts, you can post them in the chat box. I know, guys, this is a theoretical session, so it might feel a bit boring for you, but don't worry. You need to know this, because now we are in the second week, and in the second week, things will be enhanced a bit and the level will go a little bit up. So you need to give us a little bit of time and all clear. Okay, so we can move forward with the edge detection thing. Okay, so without wasting much time, what is an edge? Edge is basically a significant local change of intensity. Like I told you, when you detect the maximum point of your first derivative, you detect an edge. So your maximum value gives us the edges. So that's only edge. Now, detection of that is can be done in many ways. The ways are there in the forthcoming slides. And where are we using it? We are using edge detection to recognize the patterns, as I told you, image morphology and feature extraction. See, I told you that you can divide your image into regions, and then extract those regions and perform various operations that you want. So these are the applications of edge detection, and they are of three types: horizontal edge detection, vertical edge detection, and diagonal edge detection. And these terminologies are pretty clear with you all. So that's the thing with edge detection. Next, we have Sid with slide change. Yeah. Next, we have the utility of edge detection. So edge detection will basically allow you to observe a feature, and if you want, you can do some significant changes to that feature. And it will also help you to extract the region, as I have been repeating from quite since a while. And it will also reduce the amount of data of the image, because you are just extracting the edges. All the other portions are not required. So image data is lessened over here. And when we come to the types of edge detection, there are 3 to 4 types. It's divided into gradient based edge detection and Gaussian based edge detection. In gradient, you have Robert, Sobel, Prewitt, and Gaussian mein you are having Canny. So now, to give you more sharpened knowledge about edge detection, I would like to call on my very talented and our cool dude Sidvet for the further explanation.
Okay, I'm audible, right? I had to quit the presentation so that I could unmute.
It's all
I'm
right. You're
audible
audible. Yeah, you're audible.
and I'm looking good. Cool. So we'll get back to the presentation right from here. I hope the screen is visible again. Awesome. Okay. So thanks a lot, Ayushri. It was a wonderful explanation of filters and like basically all the concepts over here and Pranav with the convolution part. So let's get started. Okay. So what we are looking over here is two types of edge detection. First type is called as gradient based operator and the other one is Gaussian based operator. So first of all, we will talk about gradient based operator as it's in an order. So it's basically something that involves convolution over again. So there are basically three main operators that come under gradient based operators, that is Roberts, Sobel, and Prewitt. But before we dive into the more like intricate details, we would like to like cover up small topic about pixels once again and the adjacencies that they show in the intensity level. So basically, when you imagine an image with pixels, it is something like a grid, and each grid has an intensity value which is basically just a number. So whenever we call for an edge, it could be either a different combination of edges that could be regular, irregular. But when we are talking about gradient based operators, well, we would always go for straight lines. So it could be either diagonal, it could be straight, like horizontal or vertical. So thus there we have different operators like Roberts, Sobel, and Prewitt. Let's get a gist of all the operators one by one. Okay, so while the slide loads, I'll just go for like Robert gives us a diagonal one, then Prewitt and Sobel will give you horizontal and vertical. So as we see that Robert operator has a 2 by 2 kernel or mass that has been covered up by Prana very beautifully earlier. So if you observe that the diagonal pixels of the mass that is named as Gx and Gy over here will convert will give you the output of your diagonal, like either a right diagonal or a left diagonal edge. So well, that's all about the Robert operator. You perform a convolution operation using the Robert mass kernel, and you get a edge for diagonal edge, my bad. So moving on to Sobel operator. Well, if you have covered diagonal earlier, so it's time for vertical and horizontal. It is not a big deal if you keep focusing on the top right corner. There we showed the two different masks, again, Gx and Gy respectively. If you see the 1, 2, 1 and the minus 1, 2 and minus 1 have been positioned on the far top and far bottom and then far left and far right. So what it essentially does is that it calculates the difference in intensity variation, and if you get a high spike in the difference in intensity, it is termed as an edge. Well, if you can go for a certain flat surface, each of them have a similar range or value, then the 1 2 and 1 and minus 2 minus 1 and minus 1 will give an addition of almost about 0, and that would not be considered as an edge. Rather, in the other parts, if you have something like the points are over here in the image are 10, 10, 10, and 20, 20, 20, then you get a sharp intensity variation, and you can consider this as an horizontal edge. So the zero lines in any of the operator would give you which type of edge is formed. Okay, so if we focus below and the output image, you can see a very scared person or a man with very weird expression, and then we see a very detailed edge detected image output. Basically it is nothing but it has been bitwise and the output of gx and gy respectively, and then it has been combined together, so you get a very detailed image. But actually if you see, it has a lot of details, like a lot of details. It does not show any prominent edges or anything. So we'll cover that in the next slide. So if you see over here, okay, I'll wait for it to load again. uh, can you guys see the pre-bit operator slide?
Yeah, it's visible.
Awesome, awesome. So it's very similar to that of Sobel operator. If you see, it's plus one, plus one, plus one, and minus one, minus one, minus one on the other sides. And basically, you can say it's like linear filters itself, whereas this is a normal filter, while Sobel was a weighted version of the same. So it basically does the exact same thing, but you can see the output of this image. It has got only the prominent ones, like the very sharp edges have been captured. But if you need intricate details to be included in your image, then you can go for weighted filters. Well, that's the gist of all the three operators. And this one gives you the diagonals, sorry, the vertical and the horizontal respectively, as we have mentioned that gx and gy. Awesome. So I'd like to call back Pranav for Canny as detector's explanation. And guys, you need to focus on this because it is going to be used in the final project as such. Okay, here to back to you, Pranav.
Thank you, Sidway. Guys, look who's back. It's me again. And now we will be discussing a very interesting topic, the canny edge detector. So this is a very amazing tool for detecting edges in images. And this is a very special edge detection algorithm. Now, why is it special? Well, I'll answer that in a while. Unlike other single-step edge detection algorithms that you saw in the previous slides, the Sobel, the Pre-bit, the Robert, this is a multi-step edge detection algorithm introduced by John F. Canny in 1986. It has 6 basic steps. Okay, so we directly begin with the algorithm. Now, the first step is converting an image to grayscale. Now, you have RGB, BGR, HSV, any image, you have to convert it into grayscale first. All right. And next step, or step two, is to reduce the noise in our image or to smoothen it. And for that, we use the Gaussian blur technique, which will reduce the noises in our images and make it smooth. For this purpose, we use the Gaussian kernel. All right, so far so good. The next step in our canny journey is to calculate the gradient of the pixels. We use the Sobel operator to do so. What we get is edge intensity and the direction of that pixel. Now, what we get is the edge which is thick at some places and thin at others. And also, intensity levels is distributed evenly between 0 to 255, which is not uniform. Okay, so the next step is applying non-maximum suppression, which resolves our issue of thick and thin edges. It eliminates the edges which do not have potential to become noise. The algorithm will go through all the points in gradient intensity matrix and finds the matrix with maximum value in the edge direction and select only those pixels and eliminate the rest. What we now have is a thin line, but still there are some bright pixels and some less bright ones, which has to be fixed. This is exactly what thresholding does, and which is also our next step, by the way. We give two threshold values. Now let's assume we have levels from 0 to 255. Assume the lower threshold to be 100 and the higher threshold to be 200. Now all pixels with intensity values less than 100 are called weak pixels and are considered as non-relevant to our images. All the ones above 200 are called strong pixels, and all pixels between them are weak pixels, but they can be strong ones, which means they have a potential to become strong pixels. And the next step is exactly how we identify these using edge hysteresis for tracking them. What it does is it transforms weak pixels into strong ones if and only if it's connected to one of the strong pixels in the image. And thus, we have a perfect edge-detected image, all thanks to Cam. Okay, guys, now you're equipped with all the weapons that you need to decode the Cartoonifying project. And without wasting any further time, I'd like to call upon Sidway to go on with the Cartoonifying project. I hope you all enjoy. Thank you.
Okay, so far, guys, any doubts? We'll like just cover it in a gist, and then we'll move on with the cartoonifying project as a simple yes or no would do.
Any guys out?
So far, so clear.
Yeah. And the one who asked about this bilateral filter working, this bilateral filter has its working associated with the Gaussian distribution curve that we just saw in the Gaussian filter wala part. So it has its working associated with that along with a weighted average mask that we saw in the linear filtering. So that makes it a very complex process. So that's the reason that we have not included it over here because we didn't want to jumble all the things up because I know that you all have been waiting eagerly for the cartoonifying projects. So yeah, we'll focus on that. If you have any doubts, you can please post them in the chat box. And if none, then please signal us that you are pretty cool and we can move forward with the project.
Yeah, a simple yes or no, all clear would do. Yeah, that's all we need.
Thank you.
Then I guess you can continue.
Yeah, okay. Considering the time limitations we have, let's introduce you guys with our input image. Okay, so here it is. Amy Santiago from Brooklyn Nine-Nine. Okay. All the Amy fans can chill down. And if you're
She's
not a
so
fan,
cool.
then I doubt you guys a lot. Yeah, thanks, Ayushi. We all
You
know she's
should
cool.
be. She's cool.
Yeah. So moving forward to the Jupyter Notebook. I guess it's visible to you guys, right?
Yeah.
Awesome. So, like any other mini project or a project, we would need to import the necessary libraries. And what all do we need in this project would be as simple as NumPy, Matplotlib for just showing the images, and of course it's CV week, so OpenCV. So we'll just run that. And okay, so if we, I've created a basic template for you guys, and typing everything out would take a lot of time. So we'll just get over with this real quick. So if you see over here, that's a basic IMRead function where you need to post the address of the image. So I would go ahead and complete that first. So our image name is amy.jpg and it is an a folder called as input image, right? So I will paste that and will convert it as usual into from BGR to RGB and will show the image. So I think the result is visible by now, and that's our beautiful Amy again. Okay, all right. So what we have been learning throughout the session is about filters and edges. Now it's time for having a practical application for the same. So, alright, there was a very beautiful explanation by Pranav on the canny edge detection, and finally it comes into handy. So, we have converted an RGB image as always, like all the sessions we have done the same. So, we'll continue with the same nomenclature. So, we will create a new image called as edges, and it would be used as mask on the later parts. What we are essentially doing over here is that we are applying canny edge detection, and let's play around with some threshold values over here. So let's put something like 200 and 200, and let's see what kind of input output does it give. So if you see over here, it's a pretty cool output. You get all the prominent edges and everything. Let's keep playing around with a bit more so that our image is a bit light, and you can see the variation in the output as we change the threshold values. But as we have seen, that canny edge detection is a very cool method for getting your edges, but it gives somewhat of a discontinuous output, and we would like something that is a bit more well, what we can say, it's a bit continuous, it's a bit prominent over the edges, and it gives a bit bold. So what we will do is that we will just get a gray image, okay, of the original image, using the color BGR to gray. And then what we would do is that we would apply the median blur filter that Ayushri has explained. Okay, the pixels that are used for median blurring are the five nearest neighboring pixels, and hence that this is shown here as five. Okay, awesome. So how we are gonna get the edges for the mask is using the adaptive threshold method. Okay, so we will look into adaptive threshold if you guys need. So first of all, what we need to provide it with is the source image, obviously. So the source image over here is the gray image that we have converted from BGR to gray. Awesome. And then we have a max value of threshold. So as we know that the max value of threshold in gray image is 0 to 255. So the max value would be obviously 255, hence mentioned as 255. Following that, we have to mention the adaptive method. So here we are going to use the adaptive thresh mean. So the threshold value is the mean of the neighboring pixels. Okay, and you also have noticed something called as a C over here mentioned that will come in just a minute. Okay, and then we also have to mention threshold type. So what we are going to do is create a black and white image. Hence, we are using binary. So it would go either to 55 or 0. Hence, it's not mentioned like 0 is by default. Also, then we are going to use the block size, and that would be 3. What block size essentially indicates is the number of pixels used for adaptive method. Okay, so the three nearest pixels would be used to get your average or the mean. And the final value is the C value, and that's the constant that's added to the adaptive method. So, well, in the adaptive method, it could happen that your mean could be 0 at times, and to avoid certain things like getting a purely white image or a purely black image, we add a certain constant C so that it's a gray, it just stands to be a gray image and it's visible. Okay, awesome. So let's run this edge and have a look. If you see, only the prominent edges have been visible over here. Something of the background noise is also there. But most of the important aspects like the shoulder, the hand, the eyes, the facial expressions, and all the components are quite easily visible. Okay, so if you want more details, you can change these values. Like you can go for 9 block size and 7 value for C, and it would create something like this. It's quite bold, and you get all the extra details that you want. But let's reduce this a bit so that it's aesthetically more pleasing. Okay, uh, more. Awesome. This looks perfect to me. It's good for me. I'll move forward with the main thing that is going to affect our cartoonifying. That would be this magic function called as color quantization. Okay, so it's a very simple function that you can essentially look into as a region growing and region segmentation involved in both. What we have to input this function is very simple. It should first of all be provided with the sample, that's the source image, and it is note that it is very important that the input format should be in numpy's float 32 data type. Okay, this is very important as we are going to use k-means algorithm to further cluster. Okay, that is the first thing that we need to provide. Then there are n clusters, that's the k. So it's the number of clusters required at the end. Okay, so that would be the number that would be the k that's over here. Awesome. So now we will talk about the criteria that have been passed to the k-means algorithm, and those include CV term criteria EPS and then CV's dot term criteria max iter. What this essentially means that if you get hit a certain percent of accuracy, or if you have passed a certain number of iterations, that would be max iteration in this case, the algorithm will stop giving you the further iterations, and will move on to producing results as such. The next thing that we have to provide to the k-means is the number of attempts. So here we are using 10 attempts, and then you have to provide them with the flags. So what flags essentially means is that whenever you give whenever you initialize a k-means algorithm, you need to initiate it with a certain point. These points are the flags, and we are going to use random centers for each initial attempt, hence the k random center. Okay, now we are getting three outputs from this k-means, and that is RET, the label, and the center. The RET would give you the compactness of the image, and it's the sum of squared distance from each point to their corresponding centers. Okay, so it's just basic maths that you get the Euclidean square and then root it. Awesome. Then you have to look into the labels as an output. That would be your classic 0, 1, 2. That's the serial number by which they are going to be identified. And finally, the centers, the updated ones after each iteration. So that is about the color quantization. What this function is finally going to give us the result as that whenever you have certain regions of varying colors and intensity, it would categorize a certain number of pixels and make it into a particular region. Whenever a region is created, you will follow all the cells in that particular region and then provide them with the same value. Hence, it would be region segmented, and it would grow from the flags that we have provided. Okay, awesome. So let's run this color quantization function. Okay. Now we have to provide this function with the source image and k. Now we have created our mask already, and that is known as edges. So we have to go back to our original image, that is image RGB, and we also need to provide the value of k for the k-means algorithm to work. So let's use some random k value for initializing, and you can see the output is pretty clear. Okay, so if you compare it with the original image, uh, I'll wait for it to load. Just a minute. Okay, so you can see it's pretty clear. It's like very smooth transitions as it's the original image. But if you get back to the cartoonified image, you can see that all the regions have been separated out, but the transition isn't that smooth. Uh, it could be better. So let's move on to sharpening the region transition. Let's provide it with the source image as img_1. So that was the output that we originally got from the quantized image. And then the measure of blur. So let's provide it another random value and have a look. So as you can see, the very sharp transitions have been smoothened out a bit, and but the major like the prominent details of the face have been preserved. So that's the beauty of median blur actually. You can play around with the measure of blur to get yourself the appropriate amount, but I'm fine with this for now. And let's run finally into adding the mask. So what we are essentially going to do is add the mask of edges, and this is just an bitwise AND operator. So we are using the blurred image that we have originally got, and then we are going to bitwise AND with the edges. And this is our final output if you see over here. Okay, so this is what all the cartoonifying project was all about. There are different methods to get a preview. So cv2.im show with a window and the image name would also give you the same output. In that case, you won't have to convert it from BGR to RGB and stuff like that. So it would be pretty easy. And if you want to save this image, you can simply go for cv2.im, right? And you need to just paste out like the address over here. For I have a folder ready for output images, right? And then we'll go for a name, something like AV output and a dot JPEG. Okay, I just give it a run. Okay, it turned out to be false. I'll just okay, it already exists maybe. I just have another. Awesome. Okay, it got saved by mistake. I ran it twice, so it came out to be false. So this is our basically our JPEG image or cartoonified image that we have got, and well, this is the result that we originally desired. Okay, fun fact, we were originally going to try this whole experiment on my own face, but it gave me nightmares after seeing my own cartoonified image. So it's just a heads up that you guys would do on something of a character on its own rather than doing on it your own face. But of course, it's all welcome if guys want to do that. Okay, that would be it for the mini project. This is where we would sum up, and any questions would be welcome. Okay, all right, I'm done with my
Yes,
part.
guys. Any questions, you can post them in the chat box. Any feedback you want to give, anything you, whatever you feel like, you can post them.
Yeah, or else we could like even proceed with the quiz section.
Yeah.
Go on, guys, ask questions. You explained it very well.
Okay, we have a feedback. Thank you. Okay. There is a question like, how did you know to take those specific steps? Okay, so when you cartoonify, when you see any cartoonified image, you notice that only the features of that particular image or the edges are highlighted, and rest the entire thing is blurred. Like you have only the outline of your eyes or outline of the nose. All these things are present in your cartoonified image, and the rest of the features are discarded. So with keeping that thing in mind, what we did was like we used all these blur filters to remove those external features, and then we used our edge detectors to detect the edges. That was the features that we had. So this way, in this order, we figured out the steps and we proceeded it. Looking at that image only, we identified certain steps.
Yeah.
Anyone else? Okay, so I
Right.
guess, yeah.
Okay, I have posted the GitHub repositories link for this, and well, you can check it out, guys. And if you have any kind of doubts, or you can post out issues on GitHub, I guess that would do.
All right. So thank you guys. It was amazing. It was an amazing session with you all, and we enjoyed it thoroughly. So please welcome back your hosts, the narrators.
Yeah, you have been an amazing audience, and
Yeah,
we hope to see you back on Wednesday for the another session.
yeah.
Till
And
then,
don't forget to answer the quiz, guys.
yeah, quiz is important. Right,
Okay,
over to
back
you,
to the
Sakalya.
narrators.
Yeah.
Thank you so much, speakers. That was a very informative and interesting session. I hope everyone learned a lot and loved the project. Also, guys, don't forget that we have a quiz just after the session, that is right now, on the quizzes platform. So, do attend it. The links are being shared in the chat box.
Yeah, guys, I request everyone to head over to the link in the chat box and apply your knowledge you gain from the sessions, the amazing session. So apply your knowledge and fight hard to grab the top spots on the leaderboard because you're getting shout outs on our handles. So do apply the knowledge. And thanks to everyone for being an amazing audience, for joining in and attending the session. We hope to see you everyone on the next day, that is on Wednesday, with the same energy and enthusiasm. So thank you, everyone. Guys, come on, guys, turn on your cameras. We will have a group photo. Okay, where are others? Okay, so I guess the picture is taken. Is it taken? Okay, so I guess it's taken. So Thank you,
Really
everyone.
so happy, Mishu.